we will now use our technique of Lagrange multipliers to solve our first example. That example was to maximize the function f of xy equals 2x to the 2/3, y to the 1/3, subject to the constraint x plus y less than or equal to 3.78. Okay, so recall that f of xy is representing the production of widgets. We want to maximize that, subject to the constraint x plus y less than or equal to 3.78. So that meant that we had $3,780 that we could spend on compounds x and y. Each of compounds x and y costs $1,000 per ton. Now I wrote this constraint is less than or equal to 3.78 because we could spend less money than the $3,780 that we have, but clearly we're going to want to spend the entire amount, okay, in order to maximize the function. So we can really think about this constraint as being an equal. Now, we're going to use the technique of Lagrange multipliers here. Okay, so I'm going to find the gradient of f. The gradient of f in this case is going to be 2/3 x to the minus 1/3 y to the 1/3. And then the derivative with respect to y is 1/3 x to the 2/3 y to the minus 2/3. And then let's look at the gradient of our constraint g. So we need to identify that our constraint is this function g of x, y equals x plus y, which we've set equal to 3.78. That is our constraint. Okay, so the gradient here is fairly simple. Derivative with respect to x is 1, and the derivative with respect to y is 1. And so now we want to use our Lagrange multipliers equation. So that says that the gradient of f is equal to lambda times the gradient of g. Okay, well, that's going to give us two equations. Okay, so the first equation is using the first component, 2/3 x to the minus 1/3 y to the 1/3 equals lambda times 1. And then our second equation is going to equal, let's see, the y components of f and g. So that's 1/3 x to the 2/3 y to the minus 2/3. And then again, that's equal to lambda times 1. So what you see here is we have two equations involving x and y and lambda. So we have three unknowns. Okay, so we need to be able to solve to find x, y, and lambda, but we only have two equations. Our third equation is always going to be the constraint. So our last equation is the constraint that tells us that x plus y is equal to 3.78. So I'm going to set equation 1 equal to equation 2. That's how I'm going to solve for x and y, because you'll notice here that both equations 1 and 2 are equal to lambda, and so I can set them equal to each other. In fact, when solving a Lagrange multipliers problem, you can always solve these equations for lambda, and it's a technique that I recommend if you would like a straightforward step-by-step technique to work through these problems, and that is solve for lambda in each equation. That way you can set equations equal to each other fairly easily. Okay, so now if I set equations 1 and 2 equal to each other, then I get that 2/3 x to the minus 1/3 y to the 1/3 is going to equal 1/3 x to the 2/3 y to the minus 2/3. Okay, so what I'm going to do is I'm going to multiply both sides by y to the minus 2/3. That will give me a full y on this side. And then I'm going to multiply both equations by x to the 1/3. That will eliminate the x's on the left. And if I multiply the right by x to the 1/3, I'll get a full x on that side. Finally, I'm going to notice that I can essentially multiply both sides by 3. And so that leaves me with a 2 here. Okay, so I get the relationship that 2y is equal to x. And then what I want to do is I want to substitute that into my constraint. Okay, so here I'm going to look at equation 3. And equation 3 says that x plus y is equal to 3.78. Okay, but x is 2y, so I get 2y plus y is equal to 3.78. Okay, that tells me that 3y is equal to 3.78. And so now I have that y is equal to, dividing by 3, 1.26, and x, which is 2y, must be 2.52. Okay, so I've now solved. I need to buy 2.52 tons of compound x and 1.26 tons of compound y to maximize my production. Okay, so production in this case is maximized at f of 2.52, 1.26, which if you plug those in, you will get 2,000 widgets, just like I saw in my picture. So you'll recall, I'm going to kind of go back to our picture here, that we made a guess about the maximum. We said it was around 2.5 and 1.25. It turned out to be 2.52 and 1.26, very close, but we guessed that our production was maximized at 2,000 widgets, which it was. Okay, so we've now solved this problem. So you may say to yourself, well, I could have solved this problem a different way. I could have just let y equal 3.78 minus x. So I could have solved for y in the constraint. I could have substituted that back into my function and made it just a function of x. And that's what you likely did in your single variable calculus class. Okay? But I like to start with this simple example because it illustrates this technique of Lagrange multipliers. Okay? You can't just solve for one of the variables in the constraint when you have 3 variables. So in fact, now I'm going to move on to an example where we have 3 variables. Okay? And this says, find the points on the sphere x squared plus y squared plus z squared equals 4. Okay, so we have a sphere of radius 2, and that are closest and furthest from the point 3, 1, negative 1. Okay, so my goal is to find points on the sphere that are closest and furthest from the point 3, 1, negative 1. Okay, so first of all, I have to figure out what it is that I'm going to maximize. Well, I'm going to maximize a function of 3 variables, and that function has to represent distance from the point 3, 1, negative 1. So the distance between a point on the sphere, x, y, z, and the point 3, 1, negative 1 is going to be the square root of x minus 3 squared plus y minus 1 squared plus z minus negative 1, or z plus 1 squared. Okay, so I want to maximize that distance. I also want to minimize that distance because I'm trying to find points that are closest and furthest from the point. Okay, but if I want to maximize or minimize that distance, I'll notice that I have this square root there, which is going to make all my derivatives quite nasty. And so a trick that we often use in multivariable calculus is, instead of looking at distance and maximizing or minimizing that, we look at distance squared. Okay? Because if you maximize or minimize distance, you will also maximize or minimize distance squared, and vice versa. So I'm going to get rid of the square root so that we can maximize or minimize distance squared. So here we're going to maximize or minimize distance squared. Okay, so that's the function that I want to maximize or minimize. And then the question is what is the constraint? Okay, what is g of x, y, z? Well, g of x, y, z is the equation of the sphere, x squared plus y squared plus z squared, and we're going to set that equal to 4. That's going to be our constraint. Okay, so now we're going to go through the process once again of Lagrange multipliers. So we need to find the gradient of f. The gradient of f is, well, it's 2 times x minus 3, 2 times y minus 1 for the y derivative, and 2 times z plus 1 for the z derivative. And then the gradient of g, well, that's going to be 2x, 2y, 2z, the x, y, and z derivatives of that sphere. Okay, so what we're going to do is we're going to set the gradient of f equal to lambda times the gradient of g. Okay, that's going to give us 3 equations, in fact. So there's going to be the x equation. Now I'm going to drop these 2's. I want you to notice that everywhere with f and g, I've got these 2's. So I'm going to divide them out and just drop them. Okay, so that my x equation is going to be gradient of f, x minus 3, is equal to lambda times the gradient of g, which in this case is x. Okay, so imagine there had been a 2 here. Okay, and so the 2's are just going to cancel out. And that's why I'm going to go ahead and just drop them. Okay, so that's equation 1. That's for the x's. Equation 2 for the y's is going to be that y minus 1 is equal to lambda times y. And then equation 3 in this case, which is the z's, is going to be that z plus 1 is equal to lambda times z. Now, in the previous example, I told you there's always a straightforward way that you can solve these equations. You can just solve them all for lambda. Okay, but in this case, it's actually going to be a little bit more difficult if I do it that way. Okay, so in the next 2 examples, I will always just solve for lambda and then set equations 1 and 2 equal to each other, and then like 2 and 3 equal to each other. But in this case, I'm going to do something slightly different just so that you can see that there are other techniques here. Okay, so I have 3 equations, 4 unknowns, okay, because x, y, z, and lambda are unknown. So let's remember here that our 4th equation is the constraint. Okay, so here I'm going to start by solving for x. Okay, so I'm going to get x minus lambda x is equal to 3. So x is equal to 3 over 1 minus lambda. Okay. Then for y, I'm going to get y minus lambda y is equal to 1. So y is equal to 1 over 1 minus lambda. And then z minus z lambda, or lambda z, is going to equal negative 1, so that z is equal to negative 1 over 1 minus lambda. Okay? And so here, hopefully you see that x, y, and z are all multiples of 1 over 1 minus lambda. And now I'm going to use that to help me get some relationships between x, y, and z. Okay, so I will notice each one is a multiple of 1 over 1 minus lambda. Okay, that's what y is. Okay, so it turns out that means that x is actually equal to 3y, and then z is equal to negative y. Okay, and I found that that was kind of the simplest way for me to find a relationship between the variables. Now, everything can be written in terms of y. So looking at our constraint was that x squared plus y squared plus z squared is equal to 4. Okay, so that's going to tell me x squared is 9y squared plus y squared plus, and then z is negative y, so that's just going to give me a y squared is equal to 4. Okay, that tells me that 11y squared is equal to 4. Okay, so what do we get from that? We get that y is equal to plus or minus 2 over the square root of 11. Okay, what is x? X is 3 times y, so x is equal to, let's see, plus or minus 6 over square root of 11. And then finally, z is equal to minus y. So I'm going to write this as minus plus 2 over the square root of 11, meaning that when y is positive, z is negative, and when y is negative, z is positive. Okay, so here are the points x, y, and z. Okay, so we found the points x, y, and z. They are 2 over square root of 11 for y, 6 over square root of 11 for x, negative 2 over square root of 11 for z, okay, and then the negative of those as well. Okay, so those are my points. And then the question is those are going to be the those are going to be the minimum or maximum points. Okay, so what are the distances associated with those points? So if I look at the distance squared, okay, let's think about, so what is f of 2 over square root of 11, 6, f of 6 over square root of 11, 2 over square root of 11, and then negative 2 over square root of 11. Okay, so what is that? That's going to be a distance of 1.734, rounded to 3 decimal places. Okay, that's the distance squared. And then f of negative 6 over square root of 11, negative 2 over square root of 11, and then positive 2 over square root of 11, that's going to give me a distance squared of 5.316. Okay, so this first one is going to be the minimum, and the second one is going to be the maximum. Now those are the distances squared. If you want the distances, we need to do the square roots. Okay, so the square root of f at that point is going to be 1.316, okay, for the minimum, and then the square root of f, okay, for the distance there, is going to be 5.316. I accidentally wrote down the distance instead of the distance squared. The distance squared is going to be 28.266. And then the distance is going to be 5.316. Okay, so we've now found the closest point, 6 over square root of 11, 2 over square root of 11, negative 2 over square root of 11, And then the furthest point, negative 6 over square root of 11, negative 2 over square root of 11, and then 2 over square root of 11.